So our topic is about graphs, IT data structures and algorithm. Objective is at the end of the lesson, the student should be able to define graphs, to identify the different types of graphs, to differentiate directed and non-directed graphs, to define directed, undirected, and weighted graphs, to define minimum spanning tree. Graphs. A graph is a pictorial representation of a set of objects where some pairs of objects are connected by links. A graph it can be represented by using an array of vertices and a two-dimensional array of edges. So one of the most versatile data structures like trees, okay? So node in a trees are vertices in graphs. So we discussed in our previous class about the trees. Lines connecting vertices are called edges. Each edge is bounded by two vertices at its end. Two vertices are said to be adjacent to one another if they are connected by a single edge. So following are the primary operations of a graph. First is the add vertex, wherein it adds a vertex to the graph. Add edge adds an edge between the two vertices of the graph. Display vertex, it displays a vertex of the graph. So in a graph, we have the undirected or unweighted. A graph G consists of a set of vertices. V is used for vertices, E for edges, where each edge is associated with a pair of vertices. So usually, we write G or graphs is equal to vertices, comma, E or edge. As labeled simple graph, so we have vertex set V. The name of our G is, or the graph is V equal to 1, 2, 3, 4, 5, and 6. Okay? So edge set, which is the E or the edges, we have 1, 2, 1, 5, 2, 3, 2, 5. Then, for the 3, we have 3, 4, okay? And then 4, we have 4, 5, 4, 6. In a directed graph, same as before, or the previous one, but there is where each edge is associated with an ordered pair of vertices. So this is the directed graph, wherein there is an arrow pointed to the next direction. A labeled simple graph, or the vertex V, is equal to 2, 3, 5, 7, 8, 9, 10, 11. Edge set E is equal to 3, 8. And then we have also 3, 10. For 5, we have 5, 11. Okay. And then 7, 8, 7, 11, 8, 9, 11, 2, 11, 9, and we have 11, 10. The weighted graph. It's the same as above, but where each edge also has an associated real number with it, known as the edge weight. So, wherein there is a value, that's why we called it edge weight. A labeled weighted graph, vertex V is equal to 1, 2, 3, 4, 5. Vertices adjacent to a given vertex are called its neighbors. A path is a sequence of edges. A graph is said to be connected if there is at least one path from every vertex to every other vertex. An unconnected graph consists of several connected components. So we have this, the sample. So this is a sample of a roadmap. So the same with your areas or with your places. Diba? The map is connected with the other, let's say going to other direction. And then this one is the graph. So you will see this one. This is what we call the vertices, like I, G, F, H, B, and so on. While the edges, this is the one that is connected or interconnected with it. This will be the connection with the vertices. So connected versus non-connected graph. So if you will notice, if it is connected graph, what have you noticed if it is connected graph? Anyone? If it is connected. Hello? Hello? Are you still there?
Hello po, yes, ma'am.
Okay. So what have you noticed if it is connected graph or non-connected graph? What's the difference between the two?
Kasi ma'am, hindi magka-duplicate.
Okay, it is not
Connected.
connected. So connected graph, there is a interconnection with each other, while the non-connected is there's no connection. So undirected graphs, edges don't have a direction. It can travel any direction. So means there's already a cut. Directed graphs can traverse in only in directed direction. So where the arrow goes, so that is the directed direction. Weight, number that represents physical distance or time or cost between two vertices, like what we have here. So this is the weight. 1 going to 4, we have the 5. So this is the sample edges. Vertices can be represented by a vertex class. Vertex objects can be placed in an array, list, or other data structure. Graphs can be represented using adjacency, matrix, or adjacency list. Adjacency matrix means it is the two-dimensional array in which the elements indicate whether an edge is present between two vertices. So edge is represented by weight. Adjacency list. Array of list or list of lists wherein each individual list shows what vertices a given vertex is adjacent to. So in the fundamental operation, to find out which vertices can be reached from a specified vertex. So what will happen? An algorithm that provides a systematic way to start a specified vertex and then move along edges to the other vertices. So each vertex is connected to this vertex has to be set at the end. So we have the two common approaches using for this vertex. The depth first search and the breadth first search. So for the depth search first application, so display visited edges. For example, reduce paths and pins in VLSI. So VLSI means very large scale integrated design and fabrication. So you will notice here a minimum spanning tree wherein there is an extra edges. So you will notice there is D going to A, or in short, a star. inside the edges. So while this minimum number, okay, so it's just like one direction, A going to B, B to C, C to D, and D to E. It's minimal, okay? So each list structure, each vertex object contains a label for that vertex. So each object contains a label for that edge as well as the two references. So one of the starting vertex and one to the ending vertex of that edge. So in an undirected graph, the designation of starting and ending is necessary. So for you to know what the vertex is. Surprisingly, if you implement this two lists, with double linked lists, our performance many operation is quite reasonable. So first, accessing information about the graph such as size or the number of vertices. So it can be done in constant time by keeping counters in the data structure. Second, one can look through on all vertices and edges or OE time respectively. Insertion of edges and vertices can be done in time assuming you already have access to two vertices you are connecting with an edge. So it's just like you are connecting the two edges with the use of, connection of two vertices connecting with an edge. 4. Access to edges incident to a vertex takes OE time since all edges have to be inspected. So we have here the agency matrix structure. Certain operations are slow using just an adjacency list because one does not have quick access to incident edges. We can add to adjacency list structure wherein it is a list of each edge that is incident to a vertex stored at that vertex. It gives also the direct access to incident edges that speed up many algorithms. So one of the example of this is the Dijkstra algorithm, wherein that will be the next discussion. Agency metrics. The standard adjacency matrix stores a matrix as a 2D array with its slot in AIJ, being I is there an edge from vertex I to vertex J, or storing a 0 otherwise. So this is the graph. We have example of 1, 2, 3, 4, 5, and 6. So if you will notice, okay, so this one is the vertices 1, 1, we have 0, 1, 2, we have 1, okay, 2, 3, we have 1, and so on. So yun yung, this one, guys, is the counterpart. So let's say the row 1, okay, and then the column 1, this is column 1, the row 1, we have 0. Row 1, column 2, we have 1, and so on. So can have a more 0, 0 design. Each entry is the array is null if no edge is connecting those vertices. So, or an edge object that stores all necessary information about the edge. So, although this is very easy to work with mathematically, they are more inefficient than adjacency lists for several tasks. For example, you must scan all vertices to find all the edges incident to a vertex. So, like this one. 1, 1, you will get 0. In 1, 2, you will get 1. So, this one. 1 going to 2, of course, there is the, what's this? the edges. So we have 1. 3 and 1, okay, you will get 0 because the position of 1 is here and then the 3 is here. Same with 4, 0, 4, 1, so you will see 0. 5, 1, okay, so interconnected, that's why you will get 1. 6 and 1, okay, no connection, you will get 0. So let's say for number 2, we have 2 and 1, you will get 1. 2 and 2, 0. 2 and 3, okay, you will get 1. 2 and 4, 3 and, I'm sorry, we're only on 2. 2 and 4, 0. 2 and 5, 1. 2 and 6, 0. Can you follow, guys? Hello?
Ma'am, yes, ma'am.
Okay, very good. So you know how to get this 3, 4, 5, 6 already? So like this 3. 3 connected to 1? Yes or no? Hello?
Hello po.
Okay, is 3, what will you get the answer? 3 and 1?
3 in 1, 0.
0. 3 and 2?
3 into 1,
Okay, so 3 and 3?
0.
3 and 4?
1.
1, because there is connection. So you know now the differences wherein it adjacent the vertices and using their edges. Got it? And the rest will follow. Okay, so if you will notice for C, 6, since this is the last number, okay, 6, 1, definitely 0, it's 2, 4. 6, 2, 0, 6, 3, 0. So what will you get only with the value? Only? What number?
The value of
What only the value that you can get? What number? What vertex? Vertex 4. Diba? Kasi yung vertex 3, 2, 1, and 5, or there's no connection with vertex C. Got it? Getting the table? The matrix?
Yes,
Okay, very good. So, continue. Okay guys, pag na-disconnect lang tayo, login ulit kayo, ha? Hello? Okay, a path of length n from vertex V, base 0 to vertex V, n is an alternating sequence of n plus 1 vertices and n edges, beginning with vertex V0 and ending with vertex Vn, in which edge I is incident upon vertices, wherein Vi minus V1 and Vi. So the order in which these are connected matters for a path in a directed graph in the natural way. So you will see here the path. So the interconnection of the vertices with their edges. So a connected graph is one which any pair of vertices in the graph is connected by at least one path. So this one, interconnected with at least one path. So you will see here, guys, another graph wherein it is connected with each other. A weighted graph associates a label or the weight with every edge in the path. So like this one, A to B, the weight is 1. B to E, the weight is 10. The weight of a path or the weight of a tree in weighted graph is the sum of the weight of the selected edges. So how we'll do it? The function distributed, we have V stands for vertices and W is for the weight. The function distribution VW, where V and W are two vertices in the graph, is defined as the length of the shortest path from V, okay, to W. So distributed B and E is equal to 8. So a subgraph. A subgraph, a graph G, okay, is equal to B apostrophe comma E. Is a subgraph of G is equal to vertex E if vertex is, and what is this? A subset of B, E is subset of E. So, and for every edge, E apostrophe is a element of E. If E is incident by on V and W apostrophe, then both of these vertices is contained in vertex. So a simple path. You will see here, guys, a simple path wherein 1, 2, 3, 4, 5, 6 is one that contains no repeated vertices. A cycle means a path of non-zero length from N to the same index with no repeated edges. So you will see here, okay, 2, 3, 4, and so on. A simple cycle, a cycle with no repeated vertices except for the first and the last one. So which is the first and last. A Hamiltonian cycle. A Hamiltonian cycle is a simple cycle that contains all the vertices in the graph. So we have 1, 2, 3, 4, 5, 6. A Euler cycle is a cycle that contains every edge in the graph exactly 1. Note that a vertex may be contained in a Euler cycle more than once. Typically, these are known as Euler circuits because a circuit has no repeated edges. So if you will notice here, on the right side, we have the first, okay, second direction, third, fourth, okay, then we have this is the fourth, fifth, okay, and then sixth, and so on. So you will see here, guys, ang interconnection niya is what? So 1, 2, 3, 4. Asan ang 5 natin? So this is your 5. Okay, after that, 6, 7, 8, and 9, 10, 11, 12 directions. Interestingly enough, there is a nice simple method for determining if a graph has an Euler circuit, but no such method exists to determine if a graph has Hamiltonian cycle. So the latter problem is a NP complete problem. In a nutshell, this means it is most likely difficult to solve perfectly in a polynomial time. So this one, we have the different types of graphs. The complement of a graph, G is a graph G. Apostrophe which contains all the vertices of G, but for each node that exists in G, it is not in G, apostrophe, and for its positive edge, not in G, is IS in G+. So like this one, we know already how to get this. Two graphs, G and G apostrophe, are isomorphic if there is a one-to-one correspondence. Vertices of the two graphs such as the resulting adjacency matrices are identical. Okay, so if you will see 1 is to 2, we have 1, 1, 3. Okay, here 1. So this is row 1, column 2. 1 and 2, you will get 1. 1 and 3, 0. 1 and 4, 0. 1 and 5, okay, since there is a connection, you will get 1. And then 1, 6 is 0. What about 2, 3? So 2, 3 is 1. 2 is to 4, 0. 2 is to 5, 1. 2 is to 6 is what? So 2 is to 6, you will get 0. What about 3? 3, so you will notice we didn't include na the 3 because automatic you will get 0. So 3 is to 4, we have 1. 3 is to 5, 0. And 3 is to 6, 0. 4 is to 5, we get 1. 4 is to 6, 1. And then 5 is to 6, we get 0. Got it? Can you follow, guys?
Yes, ma'am.
Okay, very good.
Yes, ma'am.
Okay, what about this? 1 is to 2. Oh, anybody? You do the answer, guys, with this, with the second graph that we have. 1 is to 2?
0.
0. 1 is to 3?
1.
1. 1 is to 4?
1.
1. Here, 1 is to 4. 1 is to 5?
Zero.
Although you will see there the answer, but you have to know how to get it. Diba? 1 is to 5, you will get 0.
0.
1 is to 6, 1. How about
1.
2 is to 3?
0.
3. 2.
Here,
0.
2 is to 3, 0. 2 is to 4?
2 is to 1.
2 is to 5? 2 is to
0.
5, 0. 2 is to 6?
1.
What about 3 is to 4?
3 is to 4.
3 is to
Yes.
4? 0.
0.
3 is to 5?
1.
3 is to 6?
1.
Okay. 4 is to 5? 4
0.
is to 5, 0. 4 is to 6? 0. 5 is
0.
to 6?
1.
Very good. Can you see? Can you do it now, guys? You know how to use the complement of the graph. Okay? So when we said this one, by the way, okay, you will see the apostrophe means that's the complement. Okay? So user, this one. Diba? You will see G apostrophe. So that means complement. Graph coloring. For graph coloring, we will deal with the unweighted or the undirected graphs. To color a graph, assign a color to its vertex such that no two vertices connected by an edge are the same color. Thus, a graph where all vertices are connected, a complete graph must all of its vertices colored separate color. All bipartite graphs can be colored with only two colors, and all graphs that can be colored with two colors are bipartite. To see this, simply note that the color bipartite, okay, graph by simply coloring all the vertices in V1, one color, and the vertices on the other color. So this one, okay, the U and the V, undirected graph, okay, and with the vertices. So given a two coloring of the graph, simply separate the vertices by color. putting all blue vertices on one side and all the red ones on the other side. These two groups specify the existence of sets B1 and B2 as designated by the definition of bipartite groups. So, chromatic number. This is the minimum number of colors that is necessary to color a graph. Interestingly enough, there is an efficient solution to determine whether or not a graph can be colored with two colors or not. But no efficient solution currently exists to determine whether or not a graph can be colored using the three colors. So we have what we call the DFS or the depth first search. So we have the rule wherein the first one, search down a path from a particular source vertex as far as you can go. Second, when you go to further, backtrack to the last vertex from which a different path could have been taken. Third, continue in this fashion, attempting to go as deep as possible down each path until its node has been visited. So the most difficult part of this algorithm is keeping track of what nodes have already been visited so that the algorithm does not run on infinitum. We can do this by leveling its edge. So to prove that this algorithm visits all our vertices in the connected component of the graph in which it starts the following. Let the vertex U be the first vertex on any path from the source vertex that is visited. So that means that W is connected to U was visited. But by the algorithm given, it's clear that if this solution occurs, U must be visited, contradicting the assumption that U is visited. Okay? Next, we must show that the algorithm terminates. If does not, then there must exist a search path that never ends. But this is impossible. A search path ends when an already visited is a vertex is visited again. The longest path that exists without the revisiting a vertex is of length v, the number of vertices in the graph. So it can be implemented with a stack to remember where it should go when it reaches a dead end. So DFS goes far from the starting point as quickly as possible and returns only if it reaches the dead end. So that means the DFS, guys, is it goes anywhere as quickly from the start. So if it is already end, so that's the time it will stop. Use in simulation of games. So there are three rules like this one. Starts with an index. R1, rule number 1, it says there, go to any vertex adjacent to it that hasn't yet been visited. Okay, so have 1, A to B1, 2, B to F, and then 3 is F to H, then C, D, G, I, E. Okay? If can't follow R1 or the rule number 1, then possible pop up a vertex of the stock. Rule 3, if can't follow row 1 and row 2, that means you're done. So what have you noticed here, guys? Are we done with this? So we passive, we start from the A. You have to start with a vertex. So this is the vertex. As long as you follow, okay, you pass all, that means you're done. If not, you have to continue. Got it? Hello? Can you
Yes,
still
ma'am.
follow? Okay.
Yes, ma'am.
The first search steps start with a vertex, visit it, push it on a stack and mark it. Go to any vertex adjacent to it that hasn't yet been visited. If there are no unvisited nodes, pop a vertex off the stack till you come across a vertex that has unvisited adjacent vertices. So like this one, guys, as I told you. Okay. So 1, 2, 3, 4, 5, 6, okay, 7, 8, 9. Now, would it be possible for us to do it, let's say D to A? Is it possible? Yes or no? Hello? Am I still connected? Hello?
Yes, ma'am. Yes.
Okay, would it be possible to pass from D to A? Yes or no? Pwede pa ba? Nabisitahin natin si D to A? Like this one, we visited the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. Would it be possible? Let's say I'm going to visit A to C. Will it be yes or no?
No, ma'am.
Yes or no? Do I have to visit? It says here, start with the vertex, visit it. So started with a vertex, visit it, push it to the stack, and mark it. Go to any vertex adjacent. So what will be the next? That hasn't yet been visited. So all you have to do is, if it is not yet visited, you have to go to the next. So now, my question is, do I have to visit A again from letter D to A? Let's say, instead of going to the right, I'll go to the left. Would it be possible? Yes or no?
Parang no, ma'am.
No, because A was already visited. Diba?
Yes, ma'am.
So, you should visit only the unvisited vertex. Got it? So what
Yes, ma'am.
about the breadth first search implemented with a queue? Queue means what? Waiting, diba? So stays as close as possible to the starting point. Visit all the vertices adjacent to the starting vertex. The basic idea, we have successive round and continue with our rounds until no new vertices are visited on a round. So for each round, we look at its vertex connected to the vertex we came from. And from this vertex, we look all the possible connected vertices. This leaves no vertex unvisited, because we continue to look for vertices until no new ones of a particular left are found. If there are no paths of length 10 to a new vertex, surely there can be no paths of length 11 to a new vertex. The algorithm also terminates since no path can no longer than the number of vertices in the graph. So the idea in breadth first search is opposite to a deep first breadth. Instead of searching down a single path until you can go no longer, you search all paths at an uniform depth from the source before moving onto the deeper paths. Once again, we'll need to mark both edges and vertices based on what have been visited. In essence, we only want to explore one unit away from a search node before we move to a different node to search from. All in all, we will be adding nodes to the back of a queue to be ones to be searched from in the future. In the implementation of the following page, a set of queues are maintained. It's storing a list of vertices, a distance of I edges from the starting vertex. One can implement this algorithm with a single queue as well. So steps, start with a visiting vertex. So what is the visiting vertex natin? We have, again, letter A. Visit the next unvisited adjacent vertex. So what is the next? Letter B. Visit the next unvisited adjacent vertex and then mark it and insert it into the queue. So next is, if there are no unvisited vertices, remove a vertex from the queue and make it the current vertex. So you will see here, guys. So A to B, we mark it 1, and then B to C, C to D, D to E, E to 7. Sorry, F. F to
D,
G,
G.
okay. G to H,
H,
and then H to I.
I.
Okay, continue until you reach the end. So, it's a opposite of the depth first. Diba? Kasi if you will notice here, guys, here, diba sa depth first search, if we visited A, B, and then we'll go with the F and so on. Okay? Directed graphs. We have the traversal. Both of the traversal, BFS and BFS, are essentially the same on a directed graph. When you run the algorithms, you must simply pay attention to the direction of the edges. So where your edges or the direction goes. Furthermore, you must keep in mind that you will only visit edges that are reachable from the source vertex. So we have mark and sweep application for garbage collection. So let's have the sample. A MarkBit is associated with its object created in a Java program. It indicates if the object is live or not. When the JVM notices that the memory heap is low, it suspends all threads and clears all marked bits. To garbage collect, we go through its live stock of current threads and mark all these objects as live. Then, we use the DFS. What is DFS? What is DFS? Depth first search. To mark all objects reachable from these initial live objects. In particular, each object is viewed as a vertex and its reference as a directed edge. This completes marking all live objects. Then, we can scan through the memory heap, freeing all space that has not been marked. So, that's the end. Guys, thank you for listening.